Welcome to our first lecture presentation about scatterplots and the mean and the variance functions. The primary method that we're going to be using to understand and visualize data is going to be the scatterplot. And the basic objective of our class is to understand how a response variable designated with y is explained or relates to a predictor variable x, or maybe to a set of predictor variables x1 to xp. And so we will primarily focus on the case where there are two continuous quantitative variables, the response variable y and a predictor variable x. And the graphical display that we use for that is the scatter plot. And what we do is we put a value of y on the vertical axis and a corresponding value of x on the horizontal axis. And in the third bullet here on overhead number 3, I have the index subscript I to designate which data value is being plotted. The scatter plot is very, very useful. It lets us see the direction and the strength of a relationship between two variables. In a scatter plot, we can also understand and communicate the relationship through two functions, a mean function and a variance function. And those are the basis for discussing the content in this section. Here's our first example. That's also described in our Applied Linear Regression textbook. It's mother and daughter heights from a previous century, and this is a built-in data set in the ALR4 package. And on this overhead I have the code that is used to get the data and plot the data. And what you can see from the display is we've got daughter's heights measured in inches on the vertical axis, and we have mother heights measured in inches on the horizontal axis. And each individual open dot here responds to a mother-daughter pair. And so, for example, this data value way out here is from a mother that is a little bit over 70 inches tall. She's the tallest mother in the data set, and oddly, strangely, not surprisingly, that mother had quite a tall daughter, also over 70 inches of height. And the R coding for doing this is to invoke and bring into recent memory the data set called heights. And we use a plot command with the response variable d height for daughter's height on the vertical axis, and then this tilde wiggle symbol to designate as a function of the mother's height. The data frame is the data frame called heights, and we give an informative vertical axis y label and a horizontal axis x label. And so you can see from this that you get the basic positive association. Mothers that are taller tend to have daughters that are taller. Mothers that are shorter tend to have daughters that are shorter. Here is another command that is going to be used in our class for producing scatter plots, and this is the scatterplot command, and it's structured very similarly. Daughter's height, the y variable, the response variable is first, and then we use the x variable, m height, for the other axis. And you can see without any special y or x variable labels, we have just the variable names m height and d height, whereas on the previous overhead, on overhead 4, we have informative labels which we supplied to the command. There are other R codings that we can use to make scatter plots. Here's one that uses the ggplot2 library, and these commands in the ggplot2 library are very high quality and produce publication type quality graphics. Here is a slightly different command using the data frame of heights and the y variable and the x variable designated that we want to put points, and we want to name our scales. So just another way that you might see graphics in the course. One of the main things that we want to discuss in a scatter plot is something that's called the mean function. And we designate that mathematically with the symbol E, which means expected value. And so what we're saying here in this overhead is the expected or average value of y given or as a function of x. And so what we're saying is the mean value of y when the predictor variable is little x. And so we're talking about how the typical value of y changes across the values of x. And this behavior could be all sorts of things. It could be constant. It could be that it doesn't matter what value of x is, y is always going to take on the same typical value. And that's what I would mean by a flat horizontal line. We could have an upward or downward sloping line, a little bit like what we see in the mother and daughter heights. It looks like maybe the mean function here is possibly increasing at a constant rate, and that would be something that would be called linear regression, which we're going to talk about in future parts of this course. A straight line mean function is another possibility. Another very common possibility is mentioned in this last bullet. If maybe y variable, the response variable, changes in a curved pattern as x changes, and that might be a nonlinear mean function. So we're talking about typical behavior of y, and in order to graphically see the mean function and visualize it, the most common method we use is called a smoother. And what happens with a smoother is we start on the horizontal axis and we take a little moving window of a few values of x, and for those values we calculate an average value of y. And then we move along the x-axis maybe a little bit bigger values, and we take a set of x values a little bit farther along the x-axis, and we calculate another average value of the y variables that the y values that corresponded to those values of x. And as we move along the x-axis, we create different average values of the y values, and this connection of average values of y is called a smoother, or a low s smoother, and it maps out a average value of y function. Here's an example of one for the mother and daughter heights data that we saw earlier. And so what is happening here is we've superimposed a red curve over the top of this scatter plot to designate an approximation for the mean function. And this red curve came from taking a local set of mother's heights that are fairly small and calculating the average daughter height in that moving window. And as we move along the mother's heights, the average daughter's height is traced out in this red line, only using the data values that we find in this scatter plot. We use a scatter plot command that's very similar to what we used to just graph the points, but now we've added some options to have smoothing. Smoothing equals true, and the span and the line width give us control over how the line and the mean function is represented. And so from this graph we can see very clear evidence that as mother's heights go up, the corresponding daughter's height also goes up, and it looks like this mean function is almost a linear mean function. It almost looks like a same kind of amount of increase in daughter's height as a mother's height would increase. There are other functions to get a graph of the mean function as well. Here's one using the plot command and a lines command in R for doing the same kind of operation. I just want you to know that there are many coding options in R to create the same kind of display. Here I don't have a red solid curve, I have a dark black dashed curve, displaying the same kind of information. And in this overhead you can see the low S smoothing command used explicitly. Here is the same kind of information from the ggplot style of graphics, where the dark blue or purple line curve shows an approximation for the mean function. And it's pretty clear from this smoothed blue curve that daughters' heights tend to go up as their mother is taller. The daughter is also taller. Another important function that describes the relationship between a response variable y and a predictor variable y is the variance function. And this is about how much variation the response y values have as we move across the values of the predictor variable x. One possibility, as mentioned in the second bullet, could be that there really isn't any change in variation as you move across the value of x. Pretty much the vertical spread in the points is the same no matter where you are on the x variable. And that would say that the daughter's height variation is about the same no matter what the mother's height would be. That's the case I'm talking about in the second bullet. The other possibility could be that the variation in the y variable changes as we move across the values of x. And so one way to communicate this variation aspect is through the variance function. So we're thinking about a function that measures the variation of y at values of x. So this is a measure of variation of y, but it's a function of the value of the predictor x. On the last bullet, we just note that we typically are going to talk about variations in statistics in terms of standard deviation. This function really is about the variance, which is just the square of the standard deviation. And we can visualize variation with an option given to the scatterplot command, and that option is spread equals true. And so that puts, I don't know if you can see it on this video, but you can see the red dashed lines that are placed above and below the dark solid red mean function. And this is an expression of the standard deviation of daughter's heights above and below the mean function. And so the distance between the mean function and one of the dashed boundaries is an expression of standard deviation. And so what I can see from this is that at about daughters that average about 60 inches of height, their standard deviation is about 2.5 inches. And so standard deviation throughout this scatterplot is that daughters tend to have about 2.5 inches of variation, standard deviation, above and below this mean function. And so I would say that the typical variation in daughters' heights is about the same throughout, no matter what the mother's height was. And this would be an expression of a constant variance function. We can see the points are pretty evenly spread no matter what the mother's height would be. And so on this particular overhead, I'm going to connect the scatterplot smoothing with variation bounds to the idea of the variance function. So notice that on the left, as we talked about, the variation in daughters' heights around the mean function looks like it is about the same, no matter what mother's height is. So look up here for tall mothers. Notice the variation in daughters' heights is about the same number of inches above and below the mean function as it is for shorter mothers. That's an expression of a constant variance function. And that's what I've been talking about in this first two set of bullets. That translates to a constant variance function. So the display on the right is showing you that the variation is about the same no matter what the mother's height is. And I've carefully put the variation to be about 2.5 inches squared. 2.5 inches squared is about 6.25 squared inches, and so that's why this variation is at about 6.25 no matter what the mother's height is. Here's another set of data from West Bearskin Lake. This is also a data set in our textbook, and here we have age of fish, smallmouth bass, on the horizontal axis. 1 year of age, 2 years of age, and so forth, up to 8 years of age. And on the vertical axis, we have the length of these fish, and I believe these would be in millimeters. And so you will notice on the scatter plot that we have dots and fish values that are very very vertically striped, and that's because we only have fish that are measured at whole number integer values of age, and that's why these things form stripes. So in a fish that are 4 years of age, you'll notice there's one fish that's about 275 millimeters, and there are other ones spread throughout the length range. I suppose that poses a good question about how do we know how old a fish is. We can't just take a look at their driver's license and get an age check on them, but you can take a scale from a fish, and fish scales have growth rings that you can count just like tree rings, and so that's where we get this from. Okay, that's enough wildlife biology. Notice that for this display we have almost a linear mean function. The dark red mean function approximation looks like it's almost a straight line, meaning that the fish tend to grow about the same number of millimeters every year. It looks like it is about 250 millimeters roughly every year, and it looks like the variation around the mean function is about the same no matter how old the fish are, and that would suggest roughly a constant variance function. And so on overhead 16, I mentioned the fact that the mean function in the dark red solid line looks like it is certainly increasing. As fish get older, they get longer, and that the amount of length growth is about the same every year, so that's basically a linear mean function. On the next display, I note that the variation is about 250 millimeters, at least in standard deviation terms. Oh, I'm sorry, that's about 25 millimeters of standard deviation, or 30 millimeters, and so I'm proposing that the variation is about 30 squared, or 900 squared millimeters, and so we have basically a constant variation across age. So the variance function is displayed over here on the right, and I've gathered the information about the variance from this smoothed red dashed distances between the mean function and the standard deviation bounds. Here's another data set from the third edition of our textbook, the ALR3 data library in R, and it's some transactions. And so what we're displaying here is the time in minutes that it takes for a bank branch to process customer transactions. And on the horizontal axis, the predictor is T2, which is the number of transactions of type 2, maybe deposits or withdrawals or some sort of activity that is of type 2. I don't know what kind of transaction that was from the data set. But what you can see here is that the data values, the open circles, represent branches of a particular bank in Australia, and the vertical axis is how long it takes the tellers to service the needs of the customers that come into the bank, and the horizontal axis is the number of type 2 transactions. And what you can see from this display is that the more transactions of type 2 that are processed, that bank branch tends to have more time consumed by tellers processing customer transactions. And that makes sense because there's more of type 2s, and so therefore it tends to take more time to process customer requests. The mean function looks like it is clearly increasing, and it looks like it is increasing in a linear fashion. More type 2 transactions tend to process more and consume more teller time at about the same amount of teller time increase for units of type 2 transactions increasing. The important thing, though, is you can see that from the variation, that as the number of type 2 transactions increases, the amount of variation in teller time is also increasing. It's more variable for very active, busy branches than it is for smaller branches that have fewer transactions. So less bank branches that have less transactions down here tend to have less teller time variation than very big, busy branches. And that's a sign of a non-constant or increasing variance function. So on this particular overhead, we notice a linear increasing mean function, but also an increasing variance function. And so on this right display, I'm demonstrating that the variation in teller time is going up as the number of type 2 transactions goes up. I hope you found this helpful. I'm just going to move out of this for a moment and show you how you can learn about data sets like the ones we've talked about. So let's just invoke the ALR3 library. Let's do the AL4 library, and let's ask for a description of the data set in West Bearskin Lake. I type help WB Lake, and over in the help pane you can see the description of the West Bearskin Lake smallmouth bass data, and you can see the variables are age at capture in years, length at capture in millimeters, and some information about the fish scale. And you can see that the data came from the Minnesota Department of Natural Resources. And that's something you can do in any RStudio environment. Hope you found the video helpful. Let me know if you have questions.